Hello viewers, welcome to Exploring Technologies. In this video, I will explain about the texture classification using Wavelet Scattering Transform. So let me show you the contents which I will cover in this video. First, I will introduce this Wavelet Scattering Transform briefly, and then I will show you that how you can compute the image features with help of these Wavelet Scattering Transform coefficients. Then I will talk about the texture image databases which I have used in this proposed scheme of classification. Then I will explain the training algorithm followed by the testing procedure. And in the last, I will explain the MATLAB implementation of this classification task with the MATLAB code. So let me go ahead. But before going ahead, I recommend you to watch my following two videos. The first one is about the introduction to the wavelet theory and its application. So those who are not aware with the wavelet transform, they can watch this video. And this second video is an introduction to the wavelet scattering transform for signals and images. This is definitely required to understand the current video because the theory part of scattering transform I have covered in this video. So links are given in the description so you can watch these two videos. So now let's come to the wavelet scattering transform. It was first proposed by the Stephen Mallet in 2012. The scattering transform uses the wavelet functions of different frequencies and the low pass scaling function phi t to generate the low variance representations of our signal ft. The wavelet time scattering yields the translation invariant representation of the input signal ft without sacrificing its discriminability. The scattering coefficients obtained at different labels. They can be used as the feature vectors and can be utilized by a classifier for classification tasks. So this is what I'm going to show you in this current video, that how we can use the scattering transform coefficients for the classification of texture images. So now let me show you the basic theory that how we find these scattering coefficients. So at label 0, the low frequency wavelet scattering transform coefficients are simply found by the convolution of your signal ft with a scaling function phi t. So this is what is shown by this equation. So SL0 scattering coefficients at level 0 are obtained by the convolution of your signal f with a scaling function phi t. At level 1, the signal f is convolved with the wavelet functions of different frequencies such as psi11, psi12, psi13. So this is what we obtain. So convolution of your function f with the psi11, psi12, psi13 like that. So this is what you do in finding a wavelet transform coefficients in continuous wavelet transform CWT. So that's why they are known as the scalogram coefficients. And then a nonlinear operation, modulus, is applied on these coefficients as shown here. Okay, so you can see the mod operation. And after that, all these coefficients are convolved with a scaling function phi t to get the scattering coefficients at level 1. So you can see these are the wavelet coefficients which are obtained with the psi11. Mod operation is taken and then we find the convolution with the scaling function. So this is done for all the wavelet coefficients which are obtained previously like that. So that's why they are known as the scattering coefficients. So if we see these operations, we find that there are three basic steps to get the scattering coefficients. What are those? First, we find the wavelet coefficients. That is the first step. And then we apply the mod operation on those coefficients. That is the second step. And in the third step, we convolve these coefficients with the scaling function phi t. So that is the third step. So to get the scattering coefficients, we apply these three steps on the coefficients. So at the label 2, the wavelet coefficients obtained in the label 1 are further convolved with the wavelets of different frequencies at level 2, like psi21, psi22, psi23 like that. And then again, as a second step, we do the mod operation, which is shown in this equation. So for SL11, the wavelet coefficients for this f convolution psi 1t, I have shown these coefficients at level, second level convolution for these wavelet coefficients. So you can see that these wavelet coefficients obtained in the first level, we perform the mod operation, then we further convolve these coefficients with the wavelets at level 2, and then we again find the mod of these coefficients. So this is done for all the wavelet coefficients which were found in the previous level. Okay, so as a third step, as I said, we have to convolve all these coefficients with a scaling function. So this is what you achieve at the second level as a scattering transform coefficients. So here you can see that after the mod operation, you convolve these coefficients with the scaling function. So that is performed for all set of coefficients. So this you can better understand with this tree diagram. Here this is your function f, this is your signal. So at label 0, we get the low frequency coefficient simply by the convolution of f and scaling function phi. Then at label 1, as I have written, we find the wavelet coefficients first. So f convolution psi 11, f convolution psi 12, and so on. These are wavelet coefficients obtained with the different wavelets. Then we perform the mod operation. As you can see, for each we perform mod operation, and then all the coefficients are convolved with scaling function phi, as you can see. So these are the scattering coefficients obtained at label 1. Now at label 2, we take one set of wavelet coefficients at label 1. Then we convolve these coefficients with all the wavelets of different frequencies. Then we find the mod operation, right? And then we convolve them with a scaling function phi. So this is done for all the coefficients, this, and so on. Okay, so this is done only for, this is what I have shown only for this node. The same operation is done for this node, and so on. So here each node is expanding. Okay, so at label 2, you are getting all the coefficients which are obtained from all the nodes. Now if you want to go to the label 3, you have to do the same operation. So wavelet coefficients obtained at level 2, they are further convolved with the wavelets at level 3 with the different frequencies like psi 31, psi 32, and so on. Then you do the mod operation, and then you do the convolution with the scaling function. So this is done not only for this is done for all nodes. So here you can see that this tree is expanding very hugely at every node. So obviously it is a computational hungry, but what we achieve as the scattering coefficients, they are very capable to represent the image features. So now come to that how we can use these wavelet coefficients, the scattering coefficients as features. So for the classification task, we have taken several images. So for all the training images, what we have taken, they are resized to 200 by 200 pixels. And we decide invariance scale to be 150 by 150 pixels. So what is invariance scale, etc., that all details you can find in my previous video. That's why I suggested you to watch that. So the second level scattering transform is computed here with a 1 wavelet only per octave per filter with a 6 wavelet rotations. Okay, so again I'm not explaining these terms as I have already explained these terms in detail in my previous video. So with these parameters, for one single image, I get total 7 matrices of size 391 by 7 as scattering coefficient. So this is what I have shown. So my input is one image that is of size 200 by 200 pixel. After the scattering transform, I get these 7 matrices of size 391 by 7. So this is obtained only when you use 1 wavelet per octave per filter with 6 rotations. Okay. So these 7 matrices are combined together to form a single array that will be used as the feature vector. So I cannot use these 7 matrices as feature vector. So obviously I need a single one-dimensional array that can be utilized as feature vector. So I have to combine these 7 matrices to make a single array. All these coefficients, how they are combined? They will be combined by averaging. That I will show you in the next slides how you can do that. Although the size of the feature vector thus obtained is 391 by 1, that is not a big number, but still if you want to get a small size feature vector, then you can go for the PCA, that is a principal component analysis. So in this video, I am not going to implement this PCA because it will make this video more complex to understand. But those who are interested in PCA, they can apply the PCA to reduce this 391 to some smaller number like 70, 80. So that will be a very small feature vector, right? So let's see how we can combine all these 7 matrices to get a single feature vector. So that we will do with the averaging. So first we do the averaging in this direction, what is shown by this red arrow. I mean coefficient this, all 7 coefficients will be averaged to make it 1. So that is done for all 7 matrices. So you get these 7 columns, right? So this first value is the average of these 7 values. So that is performed for all rows. And then we do the averaging in this third dimension. So I mean this coefficient, this one, this. So these all 7 coefficients will be averaged together to make a 1. So at the last you get this single array of size 391 by 1. So that will be used as a feature vector for an image. Okay. So now let's see the image databases which I have used in this proposed scheme. So for the proposed scheme for texture classification, I have used the 2 databases. They are KTH tips and the KYBERGE. The KTH tips has the total 10 classes of texture images, and each class has the total 81 images. These images are of size 200 by 200. They are grayscale images and in PNG format. The KYBERGE has total 28 classes and 160 images per class. And each image is a grayscale image of size 576 by 576 pixels. So for the proposed scheme, we have taken fewer classes rather than all image classes to make the problem simpler. So from KTH tips, we have taken only the 5 classes with 81 images per class. They are aluminum foil, cracker, corduroy, sponge, and linen. So the samples are shown in this figure. So this first one is the aluminum foil, this is cracker, this is corduroy, this is linen, and this is the sponge. So these are example images which are in this database. And the second database is the KYBERGE. So again, we take the 5 classes with 80 images per class. So these images are lentils, rice, oatmeal, pearl sugar, and sesame seeds. So these are the samples. So this is of lentil, rice, oatmeal, pearl sugar, and the sesame seeds, right? So these are the texture images we are going to use. Now, all the images are stored in the 2 folders which are named as KTH tips and the KYBERGE. So here you can see the snapshot of that window. So we have the 2 folders. We have to create the 2 folders. One is the KTH tips and other's name is the KYBERGE. That I will show you in my computer also. All images are divided into 2 parts, training images and the test images. So I will divide all images. Out of those, 80% I will take for training and 20% I will take for testing. Okay, let me show you that how I have created these 2 folders in my directory. So let me jump to the Windows Explorer, and this is my folder where I have created these 2 folders. You can see by the name KTH tips and KYBERGE. So the KTH tips, when you open, you get 5 subfolders with the name aluminum foil, corduroy, cracker, linen, and sponge. So when you click any one of these, you will get all these 81 images. Okay, so this is how they are. All images are saved. This is corduroy and so on. And when you open KYBERGE, again you have 5 folders with the name lentils, oatmeal, pearl sugar, rice and sesame seeds. So when you open these folders, you will get these 80 images per class. So this is how you have to make these 2 folders first. Okay, so now come to the training. So this figure shows the overall training. So for the training, you have all training images. So first you have to resize those images by the size 200 by 200, because my database has a few images which are not of 200 by 200 or equal sizes. They are of few images are of different size. So the first thing is that you have to resize all images to a common size of 200 by 200. Then we take the scattering transform. So we get the scattering coefficients. So with the specified parameters, which I have explained in the previous slide, I get the 7 matrices of size 391 by 7. So then I consolidate these matrices to get a single array of size 391 by 1. So that I have done with averaging, which I have shown already. So I get a feature vector of the training image. So this I have to do for all 80% selected training images. So let's say if I have a few hundreds of images, then all images will be converted into their equivalent feature vector. And then these feature vectors will be stored in a matrix like FE1, FE2, FE3 and FEN. So this matrix is known as a feature database. At the same time, you have to create a label database also. So in label database, you will write the image name as a text string. For example, if you take one image from the aluminum foil folder, then you will write aluminum foil as a label 1. And then if you take one image from the cracker, then you have to write cracker here. So all the names will be stored as a text string in this label database. Okay. So this is done for all training images. So this is how your training is complete. Now come to the testing. So to test an image, to predict its class, we will take the query image, we will resize it to 200 by 200. With the scattering transform, we will find its scattering coefficients. We will consolidate those scattering coefficients to make a single array of 391 by 1. And that I will call it as FVQ, that is the query feature vector. So now what I will do to get the similarity, I will compare this FVQ with previously stored all the feature vectors which we obtained during the training. So that comparison is done on the basis of finding L1 distance. So this is how you can find L1 distance between the FVQ and FVI. So that is the difference D between the query feature vector and the previously stored feature vectors. So all these differences will be stored in a distance array like D1, D2, D3 and so on for n number of images. So from out of these numbers D1, D2, D3, I will select the least number. Why least? Because the least difference will give me the closest image. So I get the index of that minimum difference. For example, that D3 is the minimum, has the minimum value. So D3 is representing the closest match. So I will get the index of D3. So index number is 3. So with this 3 index, I will search the location in this label database. So obviously this is the location at the third location. So at the third location, whatever text string is written, that is my output. So for example, if aluminum foil is written there, then the class name of that unknown image is aluminum foil. So this is the testing algorithm, right? So now come to the MATLAB implementation. So to implement this in the MATLAB, I have to create these 3 MATLAB files. So the first one is the text class.m. So this is the code for the training. So here all the images in the training, they all will be converted to their equivalent feature vector and will be stored into the feature database, and their name will be stored in the label database. So the databases will be created with this text class.m. And this second file, that is a text class test.m, it is the testing code for single image. So here what you can do, you can choose a single image and then you can find its class. So that single image feature vector will be calculated and its feature vector will be compared with all previously stored feature vectors, and then with the least distance you will get its class. And the the third program, which is the text class bulk test.m, this I have written to test multiple images with the one click. So suppose you have 100 or 200 or 1000 images in a folder, test images in a folder, then you can simultaneously you can predict their classes with a single run. So with help of that, you can find the accuracy of your proposed scheme. You can draw the confusion matrix, etc., to explain its efficiency. So let me come to the code now. So this is my code text class.n, which is the training. So here I define the path where my folder is there, KTH tips, as I have already shown the folder which I have created in the directory. And this is the path for KYBERGE. So here I have made it comment because one will be executed at a time. So if you want to show this for KTH tips, you enable this. If you want to run this code for KYBERGE, you enable this and disable the KTH, right? Then with help of the image data store, I am creating this imgds variable, which will include all the subfolders and the label source, etc. These two codes I have disabled right now, but you can enable if you want to shuffle the images. You want to, during the training, you want to take any 80% rather than the fixed 80% from first to last. So here I have disabled. You can enable in your case if you want to shuffle the images for each run or each training. Then with the split each label, I have split those all images into 80% training and remaining 20% as the test images. Then I am finding the total number of images, and then here I am creating the wavelet scattering network for images with the input size of 200 by 200 and the invariance scale of 150 by 150 pixels. So the scattering network is created by this command, wavelet scattering 2. This command I have already explained in my previous video. And then I'm reading the first file from the training database. I'm resizing it to 200 by 200. And then I'm getting the features, scattering features of this image. So in the SMAT, I will get those 7 matrices of size 391 by 7. Then I'm consolidating those 7 matrices into a single array of 391 by 1. So that is going into the features variable. Then I'm getting the size of that feature, right? So with help of this size, I'm initializing a feature database matrix. So the size of the feature database matrix is number of images and the feature size. Okay, so number of images, that are number of rows, and feature size are number of columns. So because here I have to store all the feature vectors of all the training images one by one. And here I'm creating a cell array. So cell array is my label database, which will contain the image names like cracker, sponge, aluminum foil, like that. So within this for loop, what I'm doing, I'm reading those images one by one, resizing them to 200 by 200, getting their wavelet features, consolidating their features to get a single array of 391 by 1, and then storing them here in each row one by one. And simultaneously, I'm getting their labels and storing them one by one into the label database. So at the end of this program, you will get the two databases, two big matrices. One will contain all the feature vectors and one will contain the labels of those images. So I'm saving those all the workspace parameters variables into the memory. So with the save kts tips.mat, in your current directory, this .mat file will be created at the end of the execution of this program. So once this matrix is created, you can see your program ran successfully. And if you want to repeat this training for KYBERGE database, then you enable that path of KYBERGE in the starting of the program, and then enable this line, save KYBERGE.mat, and disable this ktsteps.mat. Okay, so your KYBERGE.mat will also be created after the execution of this program. So this is the training. Now come to the single image test program. So here I'm loading those .mat parameters, I mean workspace parameters. And then with this UI get file, the system dialog box will appear, and you can choose any of your unknown test image. So that test image will go into the img variable. Then you are resizing that to the 200 by 200. And then with this command, you are getting the wavelet scattering coefficients into the SMAT, then consolidating those 7 matrices into a single array using this mean and that is the FVQ, that is the query feature vector. Then you are initializing a distance array, so that will store all the L1 distances. And then within this loop, for loop, for 1 to all images, I mean number of images, what here I am doing, I am finding L1 distance. So I am comparing my query feature vector with the previously stored feature vectors. So those distances will be stored in the distance array one by one. Then I am finding the minimum distance. Minimum distance means the closest match. So I am getting the index of that. So with help of that index, I am searching that index into the label database. So in the label database, whatever string is written there and at that index, that is my result. So that is my class of the predicted class of that input image. So with this insert text, I am inserting that text on the image, query image, and showing that image with the predicted class. So very simple program. Now come to the bulk testing. So bulk testing, where I will test lots of images with a single click. So here I'm loading my database first, and then I am finding the total number of test images. Then I am creating this variable labels true. Labels true means it's a label matrix that will store the labels, I mean the names of all test images. For example, those test images are, let's say, aluminum foil, crackers, corduroy, etc. So that names will be stored in the labels true. And this is, I am initializing another string matrix, that is a label result. So this will store their predicted class. Okay, true class I know already, because I know that this is the aluminum image. So its true class is aluminum. But when I give this to the algorithm, let's see what algorithm will find it. So if algorithm find it, let's say some name, that name will be stored into the label result. So at the end of the program, I have these two string matrices. So I can compare them, that how many images are classified correctly or not. So I can compare this to get my percentage accuracy. Then I'm initializing the distance array to store the L1 distances. Then within this for loop, I'm reading test images one by one, resizing them to 200 by 200, finding wavelet scattering features, I mean coefficients, consolidating them to a single array, storing into the FVQ. And then within this for loop, I'm comparing this FVQ with the previously stored all feature vectors, and then storing the distance in the distance array. Then again getting the minimum distance and its index, corresponding index. And then with this index, okay, from the label database, I am getting its class, predicted class. And then I'm storing that predicted class into the label result. So this is the matrix which I have just initialized in the starting of the program. So all the images will be gone through the testing, the class will be predicted, and those classes will be stored into the label result. Okay, so to find accuracy, definitely, as I said, I will compare the true labels with the predicted labels. That's it. So how many labels are equal with each other? So if they are equal, so you will get the 1 1 1. For non-equal, you will get 0 0 0. So you are finding the total number of ones divided by total elements into 100. So that is a percentage accuracy. And then with a confusion chart, you are drawing that confusion matrix. Okay. So this is my bulk testing program. So now let me take you to the MATLAB where I will run all these programs to show you the performance of this implementation. So let me go to the MATLAB. So this is my editor and this is my training program. Okay. So here I have enabled only the KTH tips. If you want to do it for KYBERGE, you enable this line, and at the end of the program enable this and disable KTH tips, right? So same program can be used for KTH and for KYBERGE also. So now I will run this program. So you can run this program by pressing this run button, but here I am not running it because it will take lots of time, because there are hundreds of images and each image will be converted to its equivalent feature vector and it will be stored in that feature database. So depending on the speed of the machine, it will take time. So after the execution of this program, the two files will be created in your directory. So let me show you those files. So this is my Explorer. So this is my current directory. Here you can see these two files, KYBERGE.mat and kthtips.mat are created. Okay, so if these two files are created, I mean one file will be created one time. When you go for KTH, the KTH tips will .mat will be created. When you go for KYBERGE, then KYBERGE.mat will be created. Okay, so if this file is created, then your execution is okay. And now come to the testing. So testing I can show easily because it will avoid my training runtime. So since I'm loading those coefficients and they are already in my directory, so they are loaded immediately. So here I'm loading kthtips.mat. Okay, so I will test my images from KTH database. So let me run this program. Okay, so it asked me to choose my file. So let me choose the aluminum file. Okay, so let me remind you that these files are unknown files. These files are not taken in the training. Okay, so these files I have taken from the test folder. So when I select this file, open, I get this result. So see this result. Result is aluminum foil. So obviously it is aluminum foil, so it is identified correctly. Now run for second. I choose corduroy. So when I choose it, this is my output. So it is also identified correctly. Run again. Choose cracker. And then it is also identified correctly, cracker. Run again. Let's say linen, and it is also identified correctly, linen, right? So I have tested these images from KTH. Now I will test images from KYBERGE. So I will disable this KTH, load KTH. So make it comment and enable this KYBERGE.mat, load KYBERGE. So that is now enabled. So now I will run this program and choose one image from KYBERGE. So I am choosing lentils. So this is my output. So you can see it is identified as lentils. Run again. Choose let's say oatmeal. So it is also identified correctly, oatmeal. Now run again. Choose one more category. Let's say pearl sugar, and it is also identified correctly, pearl sugar. And then last one, that is rice. So I select rice, and this is rice. Okay, So this is how the testing of single image is done. Now go to the testing of several images at once. So this is the code. This is the third program, text class bulk test.m. So here I will take all the testing images and they all will be tested simultaneously. So at the end, I will get the percentage accuracy and the confusion matrix. So here I'm taking for KTS tips. So let me run this program and see what I have done here. In the beginning, I separated all the images into 80% and 20% group. So all the 80% images were used in the training, and the remaining 20% images now I am using in the bulk testing. So I'm running this code, and this code is running. It will take time because lots of images are used in the training. So here you can see that MATLAB is busy and it will take time. So let us wait. Okay, it is done. So here you can see that accuracy is 100%. So for all those 20% images, all are identified correctly, and this is your confusion matrix. So you can see that all 16 images of aluminum foil are identified as aluminum foil. All 16 corduroy are identified as corduroy, and so on. So here I got 100% result, and same I can do for the KYBERGE also. There I also get 100% result. So 100% is not surprising because the scattering coefficients are very capable to represent the images. Also, I have taken very simple images in the database. They all are very clear. The difficulty arises when your images are complex. If they are distorted, if they have the uneven light intensity, they are rotated something. In that case, definitely you will not get 100% accuracy. So some may be misclassified. So if you include more classes in this program, you will not get 100. But still you get very good accuracy, around like 98-97% when you take complex images. So this is all about the wavelet scattering transform, wavelet scattering coefficients as features, and how we can use these features to classify the texture images. The same program can be used for classification of other types of images, not texture only. You can use these features for classification alphabets and digits. So you can implement the OCR, optical character recognition, on the basis of this also. So you can try this sample code for classifying different category images. So I hope you have learned something new in this program. You have learned that how you can implement the classification with help of wavelet scattering coefficients. So thank you very much for watching this video. I hope you have enjoyed, you have liked this video. You can share this video to other people. So thank you very much. Thank you once again. Have a nice time.